Hello and welcome to this video about determinant proofs. In this video we'll prove this theorem. It's a bit hard to describe, but it introduces the concepts of the minor and the cofactor. This theorem leads us into proving the important theorem that the determinant of a matrix can be found using the minors of a matrix, which is introduced as the alternative definition of the determinant, but not the one used to prove all of the other theorems. It is the most complex, long and difficult of all the theorems that we'll prove so far. So here are some new concepts, the cofactor and the minor. We'll prove different things in this theorem so as to slowly build up to proving the main part of this theorem. We'll start by proving this statement. If we define two permutations beta and alpha and define beta in terms of alpha like this, then the number of their inversions will obey this equation. The number of inversions of a permutation is given by this function capital I, and we can add this parity equation to this part of the proof too. Then we'll prove this parity equation which depends on the first part of this theorem. Then we'll prove this equation which is the determinant of this minor of A. And then finally we'll prove the main part of this theorem. I guess that you see this by now as being quite a long and complex theorem. So I'll just explore some of the new concepts of this theorem. If we let matrix A be this, and if we let this matrix be a minor of A with these two subscripts, then this is what this minor is in terms of A. We'll strike out the row and column given by its subscripts. The first subscript 2 refers to the row, so we'll strike out the second row, and the second subscript refers to the column, so we'll strike out the third column, which will leave us with this smaller matrix. So this is what a minor is. Now to see what a cofactor is. We'll let this number A23 be the cofactor corresponding to the minor that we've just found. And the cofactor of A is the determinant of this minor of A, multiplied by either 1 or minus 1, depending on what the subscripts are. This gives us a number, and it ultimately gives us another way of calculating the determinant of a matrix. And in this case, we'll multiply this determinant by minus 1, and the determinant of the minor is minus 64. I used an online matrix calculator to do this. And so we'll end up with this number 64, which we can use to find the determinant of matrix A. Now to look at an example of how to calculate a determinant using minors and cofactors. We'll expand out this matrix using this other definition of a determinant that we eventually have to prove. The first sum tells us to look at each entry in the top row, and for each entry we'll get the determinant of the cofactor, which starts from the second row and leaves out the kth column, since sigma of 1 is equal to k. We'll investigate what will happen when k is equal to 1, so it's the first entry multiplied by its cofactor of this matrix. I've decided to call this function part det because it's calculating only part of the determinant, the part corresponding to the first entry of the top row. So I can write it like this, substituting the cofactor of A in for this more complex expression. So now let's look at what happens to this matrix when we try to get its determinant this way. The first entry in this matrix is 8, and this is what the cofactor of the first entry of matrix A is. And we'll write the cofactor out having gotten rid of these rows and columns. The minor that we'll take the determinant of is a smaller square matrix. And so the cofactor of the first entry is minus 380. So I'll try to calculate this determinant again using cofactors. I've copied the first entry on this page. And this is what the cofactor of the first entry is. And this is what it is with the given row and column removed. This is what the cofactor is. It's a number. So now we'll use this cofactor to find the determinant of A. And this is the part of the determinant in terms of the first entry and cofactor. Then we can substitute all of the numbers in, the first entry and the cofactor. And this is what this part of the determinant is. We'll have to find these parts of the determinant for each entry on the top row and add them together. So now we'll do a proper calculation of the determinant of matrix A in terms of the cofactors of A and all of the entries of the top row. And then we can substitute all of the values in. There isn't really enough room to show everything properly here. So I'd just like to show you this picture. It shows what the different parts of the formula refer to. The part circled in blue is the expanded top row of the matrix. The part circled in green is the parity, and the part circled in dark pink is the determinant of the minor of the matrix. And I'd like to show you this picture. As we work our way across the top row, we'll add all of the permutations in the minor matrix circled in green to the corresponding entry that's circled in blue, and so we can get all of the next order of permutations that correspond to this larger matrix. So now to prove part A of this theorem, we'll let alpha and beta be two permutations, and beta will be defined like this in terms of alpha. Beta is one variable bigger than alpha, since alpha only operates on numbers 1 to n-1, while beta operates on numbers 1 to n. Then part A says that the number of inversions in each of these permutations obeys this equation. The number of inversions function is given by a capital I. It leads into this parity equation. I'd like to try a concrete example first, and then another more generalized example. We'll let alpha be this permutation. We could calculate the number of inversions by counting how many numbers to the right of a number are less than it on the bottom line. We'll let k be 5, which is a good example, since it's in the middle where we can watch it more closely. We'll create a new permutation called alpha 1. We'll do this by adding an extra number to the end, in this case 8. And then push all of the numbers on the bottom line to the right by one space that correspond to the top line being k or greater. In this case it's 5, and then slipping the new number 8 into this position. This does change the number of inversions, but the number of inversions due to the original numbers that aren't 8 doesn't change. So we can change it again by adding 1 to all of the numbers in the bottom row and replacing 8 by 1. We can see where the number 8 is in the bottom row. It's 7 plus 1. We can see it here that it must be in the bottom row, but we won't be able to see it in the more generalized form of this permutation. So I'll just scroll everything up the screen here. So the number of inversions of the original numbers added to 1 doesn't change because they keep the pattern of which numbers are bigger than which other numbers. The number 1 that is in position k is smaller than all the numbers to the left, and so contributes a k-1 to the total number of inversions. It's smaller than all the numbers to its right, and contributes nothing extra to the number of inversions because of those numbers to its right. So in this case, k is equal to 5. So we'll write this formula down, that the number of inversions increases by 5 minus 1. And then we can write down the more general formula here, that the number of inversions increases by k minus 1. So now to look at a more general case so that we can prove it true for any permutation. We can create alpha 1 like before, by adding the number n in here and slipping it in under k. And this changes the number of inversions, but not due to the original numbers less than n. And we can add 1 to all of the numbers in the second line and change n into 1 below k. N itself will exist somewhere in this second line, but we can't find it in this more generalized case. The number of inversions of beta is changed by the number 1 and its location. It contributes to the number of inversions by k minus 1 because there are k minus 1 numbers to the left that are greater than it. We know this because 1 is the smallest number. It contributes nothing due to the numbers to its right because they're larger than it. And we can jump straight to this equation, but I'd like to explore it in a bit more detail. So I'd like to explore this statement a bit more, why this implication is true. I'd like to define this function which gives us the parity from the number of inversions of a permutation, which is a sort of in-between function. We can apply this function to both sides of this equation to get this. If this number k minus 1 is even, then this shouldn't change the parity. So if k minus 1 is even, then these parities are equal. If k minus 1 is odd, then the parity is multiplied by minus 1. And so one parity is the negative of the other. I'd like to write down what the parity of alpha is in terms of these functions par and I. And I want to do a similar thing for beta. So these parities are equal if k minus 1 is even, and they are the negative of each other if k minus 1 is odd. We can express this using this equation, which gives us the correct sign depending on k minus 1. And this number minus 1 to the power of k minus 1 is its own inverse. We'll show this by multiplying it by itself. The indice here is an even number. So multiplying this number by itself gives us the number 1, so it's its own inverse. So this formula is true too, which we'll need to use as well. So these are the actual permutations that we'll be using. They are inverses of ones used in the proof. We'll have to show that this equation is true. So now to prove it, we can use this parity equality that we've already proven before. And then we've proven this in part A of this proof. We need to substitute inverse tau in for alpha and inverse sigma in for beta. We can add 2 to this indice and it won't change it because we're multiplying it by 1. We can substitute the function tau in for the inverse of tau that we've proven in a past video. We've invoked this theorem twice now in this part of the proof. So now to prove part C of this theorem, that this equation is true for this minor of A. We'll set these matrices to have these entries. And this is what these entries are in terms of each other. You might be able to see that M is a minor of A. The kth column is chopped out, and these columns after the kth column are pushed back to fill up the space that's left. So we'll expand out the determinant of this minor of A using the definition of the determinant. We can make this substitution for the dummy variable tau by the inverse of tau in this way. The dummy variable is still tau, but the inverse of tau is used in the rest of the expression. We've proven that we can do this in a past video. We can then make this substitution. Now we're using the entries of matrix A and not the minor of A. We have a space where the kth term is missing. We can make this substitution in the parity function, because the parity of a permutation is equal to the parity of the inverse of this permutation. We've proven this in a past video, and it's been used lots of times now. So I'll just scroll everything up to make some room for more of the proof. We can define this function in terms of this other function like this. Notice that we're defining the inverses of these functions, which we can do. It's necessary to do it here because we want to substitute one inverse function for another inverse function in this part of the proof. We can invoke an earlier part of this theorem to get this result. And now we can perform this substitution. We can write out what a lot of these terms are from the table to get a closer look at what's happening. So now we'll perform this substitution, and we still don't have the kth term for A. So I'll just move everything up the screen here so as to make more room to write more of the proof. So I'll write down what I've already said, that this kth term of A is missing from the list. From the table we know that this is true, because this is how we define this function. We can substitute 1 in for k using this equation. Then we can get the reverse of this equation. We could substitute inverse sigma in for sigma, so that this first entry in the list of products would be missing from the list instead. So we'll do this substitution. And so we'll get this equation, and the kth entry of A is present, but now the first entry of A is missing. So I'll just scroll up the screen again to make room for the rest of the proof. And because all of the entries of A from the second to the nth are present, and we don't have to show the missing kth entry, then we can simplify this expression to be this. We can take this term outside of the sum, because it's a constant that's independent of the dummy variable sigma. And so we've got the result that we wanted. The determinant of this minor of A is equal to this expression. So now for the last part of the proof, which is to prove this statement, which is the main goal of this theorem. We've only just proven the other things so as to be able to prove this. So now to prove it, we'll first prove it for I is equal to 1, which is how we'd normally find the determinant of a matrix using this method. Then we'll try to prove it more generally, for I being any number from 1 to n. So we'll firstly expand the determinant of A, using the definition of determinants. We can then break up this sum into two sums. The first sum counts each entry in the top row and then multiplies it by the next sum, which sums it up for all of the permutations. But the first term in the permutation must equal k, which is the entry in the first row. Now this is what the minor of A is with these subscripts, according to part C of this theorem, so that we can substitute it in here. We can write the minus 1 to the power of 1 plus k term on the other side because it's its own inverse. And we can substitute the cofactor in here because that's its definition. So these two lines prove that the determinant of a matrix can be calculated from its minors or cofactors, which is sometimes presented as a second definition of the determinant, or as an unproven theorem in textbooks. I'll just scroll everything back up the screen here so as to make more room. So now we're required to prove this result, that if the leading subscripts in these variables aren't equal, then this expression is 0. We'll substitute this expression containing the minor of A for this cofactor. Then we'll substitute in this expression for the minor of A. We're taking the minor of jk. This means we're removing the jth row. So the first row is included in this product, circled in crimson, and we're leaving out the jth row, circled where it would have been in green. But we've expanded along the top row, circled in orange. So we've effectively got the determinant of a matrix with two rows the same, so that it's going to equal 0. We've done this calculation for this in part C, but we've modified one of the variables. If we replace 1 by j in the indices where 1 should go, then we'll get this equation. Then we'll get everything under the 1 summation symbol. So this looks like the determinant of a matrix with two rows being equal, so it's equal to 0 by a past corollary. So I'll summarise what we've found. This expression is 0 when j isn't equal to 1, but is equal to the determinant of A when j is equal to 1. So we can write it out as this case function like this. We can go one step further and write it out using the delta function, which is what we're trying to prove. But this proves it only for when the leading subscript in entry A is 1. We have to prove it for all cases, like when I ranges from 1 to n. So before I go any further, I need to prove this result, so that I can prove this theorem true for when j isn't equal to 1. I'll assume that it's true for some matrix C, and matrix A is matrix C with rows 1 and j swapped, so as to bring row j up to be the first row, and thus prove this theorem true for row j being expanded. So I'll define matrices A and C to have these entries and look like this. We'll let matrix C be this matrix with these entries. The rows are numbered in numerical order from 1 to n. And matrix A is matrix C with rows 1 and j swapped. We'll write it out in terms of the entries of C. Notice that the rows aren't in numerical order anymore. It doesn't really matter which matrix I choose to have the unswapped entries. I can still prove the same result, because this part of the proof is fairly symmetrical and can work with either matrix. This is matrix C with entry C 1k and its corresponding minor. And this is the minor of C, which is C with the appropriate rows and columns removed. This is matrix A in terms of the entries of matrix C with its entry at 1k with its corresponding minor region. And this is the corresponding minor of A with the appropriate rows and columns removed from A. I'll just write out these minors of matrices A and C, showing the location of the first row of the minor of C. That's located at the j-1th row of the minor of A. It's good to have a look at this picture. So now to have a look at these matrices in vector line notation, where long lines show how the vectors occupy these matrices, and there is a series of row swaps to get from one of these matrices to the other, unlike the matrices A and C that they were calculated from. And there's more than one row swap because more than two rows have been moved around. It turns out that j-2 row swaps are required to get from one of these matrices to the other in either direction. I won't prove this too rigorously. You can try plugging different numbers in and see the results. It might be good to prove it by induction, but this is a theorem that's already taking more than 20 minutes to prove. So because there are j-2 row swaps to get from one of these matrices to the other, then this formula is true. Each row swap multiplies the determinant by -1, and so we end up with this term -1 to the power of j-2. So I'll just scroll everything up the screen here to make more room. So this is what the cofactor of A is from the definition of cofactors. So we can combine these two equations to get this equation. We can add up all of the powers of -1 like this. Then we can simplify this expression like this. So we can get this cofactor of C from the definition. We can combine these two equations and simplify them quickly to get this equation. One of these cofactors is the negative of the other. So we can write this equation. We can substitute one cofactor for the other like this. We'll get the minus sign because one of these cofactors is the negative of the other. And these two entries are the same because matrix A is equal to matrix C with rows 1 and j swapped. So then we can make this substitution, thereby completing the result that we want. So now we'll have to prove that this quantity is the determinant of A when I isn't equal to 1. We can perform a row swap to bring row I up to the first row, and the first row to row I. So we're in a better position to use the result we used when I was equal to 1. We can put this row swap function in front of A, and let it be a matrix that multiplies by A on the left. This is the result that we proved earlier and now have to use. And this is equal to minus the determinant of C. We can put in this formula because determinants can multiply together like this according to a past theorem. And the determinant of a row swap is -1. We can substitute this in for the row swap matrix. And so this is equal to the determinant of matrix A, so we've proven this part. And finally we'll have to prove this when I isn't equal to 1. And when I isn't equal to j either, but j can equal 1. I'll just write out the statement of this proof here like this to make some more room, so as to set the proof out properly. We'll call it part F. This proof is very similar to the other proof of this quantity being 0 when I was equal to 1. We'll expand this sum out using the definition of cofactors. So now to get the determinant of this minor of A with row j and column k missing, we'll draw up a picture of this matrix here. So the determinant of this minor is equal to the sum over all the permutations of size n-1. We'll write this using the dummy variable sigma. There will be another permutation function that will be used to find the determinant of this matrix, called sigma dash. That's different to sigma, because it contains one less element than sigma. I could write it in here and it will find the determinant. So I'll use this permutation to calculate the parity. But I'll never need to know what it is, because this determinant will turn out to be 0 anyway. So it's equal to this sum with the jth row missing. J isn't included as the leading subscript in any of these sums. We'll have to show that the kth column is missing. We'll do this by setting this permutation equal to k, that we're summing it up over when applied to j. So this will cause column k to go missing in this sum. Then we'll expand the determinant of the minor out using the calculation we've just done. Notice that the jth term is missing from this sequence because the jth row was chopped out of this matrix when we created this minor from matrix A. Then we can bring everything in under the same sum. The ith row will occur twice now. Last time it was the first row that occurred twice, and the jth row is still missing. So we've replaced the jth row with the ith row. We can put the permutation sigma back inside the parity function like before, because this sum uses sigma to calculate the determinant. So this sum represents the determinant of a matrix with two identical rows, and therefore is equal to 0 by a past theorem. So this proves part F. And so we can add this result to the main proof. So finally we can put it all together and write down this statement. So we've proven this statement that we set out to prove. So I hope that you understood this proof, or that maybe you'll feel like you'll eventually understand it. It's hard to find in textbooks and on the internet, and I had to put it together from strands that I found in the textbook proof, since they left a lot of pieces out, or only half explained some other parts of the proof. If you felt that this video was helpful in some way, then please click like and subscribe. Feel free to write anything helpful in the comments and to share this video, and thanks a lot for watching.